Okay, thank you very much. So welcome to today's lecture about the axion as dark matter. Still, we are not there at dark matter, but we continue with the axion today. So I first recap the most important thing from the end of the last lecture. So I recap that the axion was essentially to replace or is a replacement of the theta parameter by a dynamical theta field. So as we said before, we had so there is a theta term in Qcd. The theta term leads to an electric dipole moment of the neutron, and the upper bound on the electric dipole moment of a neutron is very small, much smaller, as one would naively expect, so the measured theta parameter has an upper bound of the order of 10 to the minus 10, and because the theta parameter is essentially the sum of a Qcd vacuum angle and an overall phase of the quark mass matrix, this requires a very strong cancellation, and to avoid this cancellation, the Peccei-Quinn mechanism was introduced, and the Peccei-Quinn mechanism is to replace the theta parameter by a dynamical theta field. So in more mathematical terms, one adds to the standard model a Goldstone field theta of x, respecting a nonlinear realized U1 Peccei-Quinn symmetry, which is now in this language is a shift symmetry, because it acts, so to say, in the angular space. And this shift symmetry should be broken only by the coupling to the gluonic topological charge density. So this theta field couples linearly to alpha s over 8 pi chi mu nu twiddle. So this quantity, as we said, is the topological charge density in Qcd. Now, so why this solves the problem? It solves the problem because with employing this shift symmetry, one can eliminate the theta parameter of Qcd by the shift, and then the effective potential for this new Nambu-Goldstone field at energies below lambda Qcd. So if one integrates out, then this Qcd dual interaction has an absolute minimum at theta equal to 0, and thus predicts a vanishing vacuum expectation value of this field, which means because the electric dipole moment of the neutron is proportional to theta bar, or now to this vacuum expectation value of theta, there is no strong CP violation in the vacuum, and of course, associated then with this field, there can be particle excitations around this minimum. The particle excitation, the mass of this particle excitation around this minimum is given by the second derivative of this potential, of this periodic potential, and the particle itself was dubbed the axion by Frank Wilczek. So it's a pseudo Nambu-Goldstone boson. Pseudo means it has a mass because the shift symmetry is broken by this Qcd dual interaction, so to say. And this mass is parametrically suppressed by the inverse Peccei-Quinn scale. So it's suppressed by 1 over Fa. And in the numerator, there stands in a sense the square of the chiral symmetry breaking scale in Qcd. And in numbers is if Fa, this axion decay constant, or your one Pecek-Winn symmetry breaking scale is of the order of 10 to the 9 GeV, then the axion mass is 6 milli-electron volt. We have also emphasized that already alone from this, that of course, I mean, so this axion, if we now integrate out the gluons, we go really to very low energies. This axion will have couplings to the standard model inherit by this Pecek-Winn mechanism, or by the fact that that the axion is mixing with the pion. So these interactions, which it inherits directly by the Pecek-Winn mechanism, is a coupling to the electric dipole moment of nuclei, and this coefficient, this Wilson coefficient, is determined by the theory, by QCD, and there are interactions with photons, which are essentially proportional by the QCD, by the QED analog of this Qcd dual interaction, which is an F dual interaction, and this Wilson, there is a model independent Wilson coefficient, which I remind on the next slides to that, and there will be coupling. So the coupling to the gauge bosons, so to say, they are linear. But to the fermions, these are derivative couplings, because, as I said, so one requires that one has only that there is this shift symmetry, and the shift symmetry automatically implies that the low energy couplings should be derivative couplings. So, and again, so this couples, this axion, or the derivative of the axion couples to this chiral current, like this to the fermions in the standard model in general, and the model independent contribution is mainly in the coupling to nuclei and to pions, of course. So the axion, so the origin axion was visible and had an Fa, had a decay constant or a Pecek-Winn symmetry breaking scale of the order of the electroweak scale, and these kind of interactions, the predicted interactions, were so strong that it was immediately 1 or 2 years after the proposal, it was rejected or was ruled out. But later on, these gentlemen like Kim, Schiffman, Weinstein, Sakharov, this stands for this is this KSVZ, or Sitnitsky, Dine, Fischler, Srednitsky, this is the DFSZ. They produced models with invisible axions, so they introduced a further singlet complex scalar, which can get a large, or which they suppose they was getting a large wave, such that the symmetry breaking scale can be much larger than the electroweak scale. And of course, all these kind of couplings, so generically they should have these kind of coupling. So the effective theory is always looking like that, but the Wilson coefficient can be different. So the invisible axion has then the couplings to the standard model suppressed by an inverse power of Fa, which is much larger than the electroweak scale, like the Higgs wave of 246 GeV. And so this is one of the first things following that directly from the pseudos, from this scalar number Goldstone nature of this particle. And moreover, since the mass is also inversely proportional to the decay constant, all these couplings to the EDM, to the photons, to these derivative couplings, they are all proportional to the mass. So the lighter the axion, the smaller the coupling. Now, I have mentioned last time already the coupling to the nucleon EDM, which is predicted already just from the poor nature that one replaces the theta parameter of QCD by this axion field, and therefore the coefficient, this GAN gamma, or here expressed as ECNNAD times 1 over FA, this coefficient is predicted by QCD, and as I said, so this coefficient C, which naively is proportional 1 over the nucleon mass of order 10 to the minus 13 centimeter, is quite a bit smaller because it's additional suppressed by the quark, by an effective quark mass, or the reduced quark mass divided by the nucleon mass. So it's parametrically smaller. But okay, this kind of coupling will be later important phenomenology for experiments which are searching for axion dark matter via oscillating nucleon electric dipole moments, such as we will see this neutron EDM experiment at Caspar Electric. So here is the prediction of the QCD axion, as I said. So of course the coupling is proportional 1 over FA, and the constant is fixed. So so it should be on a line, and the line is very thin. And we will see one particular model where this can be where this is this line is, so to say, there's an additional parameter where one can go away from this line and have parallel lines to this. So the 1 over FA stays the same. However, so to say, the mass is, so to say, smaller for this thing, and then essentially this chiral symmetry breaking scale is replaced by something else. So that's so far about this coupling to the nucleon EDM. So this is model. This coupling is model independent. Then there's is the coupling to photons. From the mixing with the pion, the axion inherits at energy scales below the QCD scale a model independent contribution to its coupling with 2 photons. So this coupling, this GA gamma model independent MI, is equal to alpha over 2 pi FA. This is a convention times the dimensionless Wilson coefficient CA gamma model independent. And this coefficient has been originally calculated by Kaplan and Srednitsky in '85. It's given by this expression, where Z is, as always, the mass of the up quark divided by the mass of the down quark. And because this is about the up quark has about half of the mass of the down quark, so this factor is about -2. And if you do a more precise determination, it's -1.92 with an error of 4. And this is exactly so this model independent contribution is this line for the photon coupling, is this line labeled KSVZ on this plot. This plot you will also see very often. This is the photon coupling in units of GeV to the -1 over the axial mass. So this is the KSVZ model. is the UV is a UV completion which exactly gives only this Qc dual term and nothing else, so to say, as the effective interaction with the standard model at scales above lambda QCD. And therefore, so this is and then, as we will see, if you look then for other ultraviolet completions, you get also a model dependent contribution to this coupling, which is additively added to that. This photon coupling will appear very often because this is arguably the phenomenologically most important coupling, because there are many experiments searching for axions via this coupling to photons. You see, this is a very, very busy plot. I will explain later some of the bounds which one gets in this plot by today from astrophysics and tomorrow and the last day from experiments. Now another thing, of course, I mean, you have the coupling to the nucleon is also from the mixing with the pion. The axion also inherits at energy scales below the QCD scale a model independent contribution to its coupling with the nucleon. As I said, so this must be a derivative coupling to this chiral current composed by nuclei, and it's the convention to label this like it's a GAN over the nucleon mass, and this GAN can again be written as this Wilson coefficient times Mn divided by Fa, and so here are our predictions to the KSVZ. So again, the next to leading order chiral determination of this coefficient gives for this coefficient axion coupling with the proton. The model independent is minus 0.47. And the coupling to the neutron model independent is nearly so to say compatible with 0. And again, so as before, this KSVZ line is the one which has only this model independent contribution. So this is the KSVZ line, and this kind of coupling is also important for experiments searching for axions via the coupling to the nucleon, and also for astrophysics bounds on the axion arising from the coupling with the nucleon, and I will later tell about these bounds, where they come from, and so on. Now, so until now we have essentially one axion, the so-called hadronic axion or KSVZ axion, which makes these kind of predictions for couplings to the standard model as a function of the mass, or normally it makes the prediction as a function of 1 over Fa, but 1 over Fa is proportional to the mass, and therefore it makes the prediction also a function of the mass. Also, as I will tell later, so to say the coefficient itself can be, there is one model where you can even change this kind of, you have a family of KSVZ models which can all move to the left, so to say. But we are starting now with the first and maybe most simple model for the UV completion of an axion model, namely this KSVZ or Kim, Schiffman, Weinstein, Zakharov model. You see, this was from 79, and the axion itself was already introduced I think at 78 or so. So very short after the Weinberg-Wilczek axion was excluded, one had already was already generalizing the concept in order to finding a new UV completions of this Axion model, which was only a and which avoided the bounce coming from colliders by making it invisible. So in this KSVZ model, one adds to the standard model a singlet complex scalar field, sigma, which features a spontaneously broken global U1 Pecek-Win symmetry. So now it's not the shift symmetry, not the nonlinear, but now it's so to say a linearly realized global U1 Pecek-Win symmetry. And one adds, in addition, a vector-like fermion in the fundamental of color, singlet under SU2 left and neutral under hypercharge. So it's very simple. So you introduce a further vector-like quark, which has no hypercharge and has no weak charge. And now you associate Pecek-Win quantum numbers to the field such that it transforms that the complex scalar field transforms as e to the I alpha sigma. The left-handed part of this vector-like fermion transforms as e to the I alpha over 2 q left, and the right-handed like e to the minus I alpha half q right. So it's a chiral. It's a chiral charge assignment to the Pecek-Win charge assignment to the fermions. And under this condition now, we can write down the most general renormalizable Lagrangian of this theory, or of this X added part to the standard model, which we call now the KSVZ Lagrangian. So it has this just the standard kinetic term for this complex scalar field. Then it has a Mexican head potential, so a potential with spontaneous symmetry breaking. So like very similar to the Higgs potential, but now just for a complex scalar with a self-coupling, a quartic coupling lambda sigma, and a WEF or Pecek-Win symmetry breaking scale V sigma. And then, of course, for the quarks, you have this covariant derivative, which now involves just the coupling of the quark to the gluons, so as appropriate for the fundamental of color in this theory. And then you can also write this mass term for this you should say this Yukawa coupling between this QLR bar and Q right and sigma. Now, if you just check here, then sigma has, so to say, Pecek-Win charge 1. Q left has -1/2, and Q right, Q left has +1/2. So the QL bar has -1/2, and this has also -1/2. So this is a nicely invariant Lagrangian. So now we look again, so a little bit more now in this Lagrangian, what it implies. So if you now decompose the scalar field here in polar coordinates, so you write the scalar field like 1 over square root of 2, a V sigma plus plus a radial field rho of x, and then you have a field, a phase field A of x, which you normalize here by this V sigma. So you can take this as new field variables. Now this rho of x and this A of x. So the rho of x essentially describes the fields in this radial direction, and this A of x describes the field in this angular direction. And if you do this, then you see that this model features 3 beyond the standard model particles. So the excitation of the Goldstone field A of x, of this Goldstone field, and this excitation is massless at the tree level. So of course, I mean, there is no, so at this bottom of this potential, so there is no mass. So it's flat in this direction. Then you have the excitation of the radial field. In the radial field, this is like in the Higgs. So this radial field has a mass given, so to say, by the something like the radius of this valley, and this is given by this scale V sigma, and so the Higgs mass itself is determined by the second derivative in this direction. So it's square root of lambda sigma times V sigma. And you have the new fermion. As if you make this thing, you would expect, of course, then that it gets also from, so if sigma gets a VEF, this new fermion gets also a mass, which is given by this Yukawa coupling YQ divided by square root 2 times V sigma. If now this Peccei-Quinn symmetry breaking scale V sigma is very large, these two latter particles, this rho particle, this radial excitation, and this new fermion Q, are heavy, and you may integrate them out. If you are only interested that the effective theory at energy is much less than the breaking scale. In principle, we are thinking of that this breaking scale is very much larger as the electroweak scale, but we are interested in this theory above above lambda QCD, so to say. So we want to integrate out all heavy particles. So now we can first integrate out this rho field, so to say. Then this rho is essentially this rho is essentially fixed or frozen at the vacuum expectation value or this radial excitation, and then from that you get only so to say the only propagating particle, scalar particle, is this axion field. I call it already axion, but is this A field, this radial excitation. And still we have the fermion field. We have not integrated out, because why didn't be integrated out yet? Because we have still here not a standard mass term, and we know only very nicely how we do this, integrate this out if we have a standard mass term. So now how can we get a standard mass term? We can, here, so which has just the MQ, where MQ is really this YQ over square root of 2. So we have replaced this sigma by the VEF, and therefore this MQ here is just given by YQ over square root 2 V sigma. But we have still this e to the IA V sigma. So how we get rid of that? This last term can be brought to the form of a standard mass term by performing a field-dependent axial transformation. So we make the transformation now that Q left is transformed by e to the I half r a over v sigma ql, and q right by e to the minus I half a over v sigma qr. So I mean, this is an axial transformation, but we have to remember that this axial transformation, that axial transformations are anomalous. So we have this chiral anomaly in the path integral. If we change these variables, then we find by the Fujikawa method, we find that there will one will get something from a coupling of this field to Qcd dual, because this Qcd dual is hidden here. Now, so what I was saying now in verse is here that because the fermionic measure is not invariant under axial transformations, if we do this axial transformation here, then this measure will be transforming like that, and then we see from this transformation we get that in addition to the standard mass term, which you get from this transformation, you get two terms. Now one term, it comes because this A comes from the kinetic term, and one term arises from this Qcd dual transformation. So you have now this nice you have it now. The mass term is in nice form, and now you can integrate out this heavy quark Q, because this heavy quark has a high mass. You can integrate it out, and then what you are left is this kinetic term and this anomalous interactions with the topological charge density in Qcd. So in fact, so what we have now seen is that this model, which we introduced at the beginning, is an UV completion, which yields exactly this minimal hadronic axion, which we were discussing before. So you have really an axion which has just a kinetic term and this linear coupling to Qcd dual. So that this Goldstone field A of x of V sigma acts exactly like a dynamical theta parameter. It is an axion. So this is we have seen how this works. So and moreover, we can read off from this. We can really read off that the axion has a decay constant V sigma, because here we have exactly here at this point there is this V sigma, and this can then be identified with this decay constant, and its couplings of this model are the model independent couplings which we have been discussing earlier. So I think we can make a little break here. So are there, because this is so to say the simplest UV completion. So are there questions to this?
So any question?
I have a question.
Yes.
Yeah. In this model, you introduce, besides the axion as a field, also these two new fields, the Q field and the rho field. In this, Then you integrated out them because you are interested just in the low energy region below the Betty-Quinn symmetry breaking scale.
Yeah.
Okay. But if this model is true, you should see this particle maybe in the standard model, I don't know, at the loop level or not.
Yeah, but you could, of course, you could look for this at the loop level, but typically, so we will see that there is a lower bound on this new particle Q, and or on FA on this V sigma. The lower bound is is about 10 to the 9 GeV or something like that. And therefore, if they are really, really,
really heavy. I see.
It would be, so I mean, they could be anywhere, yeah. But nature has already told us that it cannot be so low.
I see.
So it's not. It's of course, I mean, originally, so this case we said, yeah, this scale FA is not predicted at all. So this is a new scale which you have just introduced by hand. Yeah. We will see later that for example, that there are grand unified models where this FA is predicted and related to the scale of grand unification. But here, so for the simplest model, it's not. It's an extra parameter, and we have to see where it is, so to say. Yeah.
But the lower limit are so high that okay, you cannot.
They are so high that it's
impossible to
don't see it in loops and so on.
Particles.
Yeah.
I see.
Yeah.
Thank you very much.
Yeah, you're welcome.
Any other question?
Okay, then I continue.
I think so. Good.
Okay, good. So now this. Okay, so this was the simple KSVZ model. Of course, we can make it a little bit more complicated, or play around a bit. So can we increase, for example, these couplings, because this has only the model independent couplings. So is there some variety in the coupling? So for example, you can say, let the vector-like quark also carry a U1 hypercharge. What is then? So then we get from the beginning also model-dependent photon coupling, so to say. So this is again the effective Lagrangian at scales above lambda QCD. There's still this Qcd dual term. So there will be then a model-dependent coupling, which arises, so to say, from the electromagnetic part of the chiral anomaly, and this Ca gamma is, for example, is 2/3 if the U1 hypercharge is -1/3, or it's 8/3 if the hypercharge is +2/3. So there's not there's not much of a difference. But other people, so like Luca Di Lucio, Meschia, and Enrico Nardi, they have investigated, so to say, how big is the variety you could take. You could exploit more general representations for the vector-like exotic fermion under SO3, SO2, and under U1. And this, if you take these more general expressions, that this will lead to a band of predictions for KSVZ-like models of the photon coupling at low energies. So the photon coupling in general will be parametric like that. And this Ga gamma is alpha over 2 pi v sigma, this model-dependent part minus the part from the mixing with the pion. Of course, there can be models where there is even a cancellation and the coupling is nearly 0. But now, they have considered a whole range of these couplings, and this is plotted here. So again, here's the coupling to the photon in units of GeV to the -1. So this is this coupling as a function of a mass, and the standard KSVZ model is somewhere. Where is it? It's E over n equal to 0. I don't know where E over n equal to 0 is on this plot. So, but they have varied this, and they have, of course, they have also realized. So some condition was, for example, if you have too many, of course, if you have too many quarks, then you can lose asymptotic freedom for QCD, and then you get lambda poles before at energies below the Planck scale. And if you take this as, for example, as a boundary, how large the presentations could be and so on, then they observed that you can establish an upper bound on this model-dependent contribution in this kind of KSVZ models, defined, so to say, by adding quarks, so to say, exotic quarks to the standard model. So this upper limit was at 170.3. So you see, they could realize an enhancement, so to say, of the coupling by a factor of 50 or so, 170 over 3 or so, over the standard case, so to say. Now, does this exhaust all the possibilities? No. Last year, my PhD student Anton Sokolov, he found a very nice, he had a very nice idea, which turned to be which turned to be giving even a much higher photon coupling. This was based on the following thinking. You may expect to get an enhanced photon coupling if this exotic quark. So of course, in order to solve the strong CP problem, that it must carry this exotic fermion must carry must carry SS3 charge. So maybe it should be in the fundamental or in other representations. But he said we expect enhanced photon coupling if this exotic quark carries also a magnetic charge. Why? Very simple. I mean, the qualitative reasoning goes as follows. So I mean, the Dirac quantization condition, namely that implies a minimum magnetic charge of an abelian monopole. So in the standard model, an abelian monopole should have a minimum magnetic charge of size 6 pi over E. So and E is small, so this minimum magnetic charge is large. So and therefore, so if this works with the anomaly, then one expects an enhancement in the photon coupling by a factor alpha magnetic, so which would be defined by G magnetic squared over 4 pi divided by alpha, which is E squared over 4 pi, equal to 9 pi over alpha squared, which is of the order of 10 to the 5, because alpha is 1 over 1 divided by 137. So and this motivated us to do a detailed calculation, and the calculation is a bit cumbersome because you have to calculate the anomaly in quantum electromagnetodynamics, but it can be done in quantum electromagnetic dynamics. And in fact, what we found is that one gets that this anomaly, this coefficient of A over V sigma arising from integrating out exotic quark, which has this minimum magnetic charge of 6 pi over E, that this goes like, is enhanced, so to say, compared to the standard case by a factor of 27 over 2 alpha squared, which is really of the order of 10 to the 5. Which means really now again we have here this photon coupling as in units of GeV to the -1 versus the mass. Here this red line is the KSVZ, the standard KSVZ model. And now if we have this standard KSVZ model, but this if you assume that this right-handed, this exotic vector-like quark carries this kind of magnetic charge, then this will be enhanced to this line. And you see, this is really spectacularly larger. Now, of course, so who has ordered such an abelian monopole? But there are different considerations which lead to which may lead to be convinced that there should be at very high energies there should be also magnetic where there should be also magnetic monopoles, and they could, so integrating out these magnetic monopoles, they could boost this photon coupling by a huge factor. And this would mean, as we will see later on, that one could have an alpha with some experiments which are only sensitive far outside for photon couplings, far outside this normally considered band of axion models, that they could also that if they find some particle, that this could be even the Qcd axion. Also, it's so far away from this standard axion line fields, yeah. Okay. Then I go to another standard model of axion physics. This is the Dfset model. It should be rather called ZDFS model, because Sydnitsky published it first, but it was totally in Russian. So the authors from the States, they were not aware of this paper, but it was first, so to say. In this model, one adds to the standard this model features a more complex scalar sector. One adds to the standard model not only this extra singlet complex scalar field, but one adds even a second Higgs doublet. So in fact, one is considering a 2 Higgs doublet model of type 2 in this as an extension of the standard model Higgs sector. In this case, one does not need to introduce extra fermions in order to have a Peccei-Quinn symmetry, to associate Peccei-Quinn quantum numbers to the fermions and to get an anomaly. Everything works just with the standard model fermions, or with the standard model quarks, in order to get this anomalous coupling to Chi dual. One of the motivations for such a model is, of course, for example, the minimal supersymmetric standard model. In the minimal supersymmetric standard model, you have to enlarge the Higgs sector to a 2 Higgs doublet model Higgs sector. And also, if you want to do a grand unification, you also enlarge this Higgs sector into a 2 Higgs doublet model of type 2. So this kind of DFSZ model can be so to say embedded into MSSM and into grand unified theories and so on. Now, then you assume, so you have this, as I said, you have a 2 Higgs doublet model, you have the sigma field, and you have the standard model fermions, and you associate to the Peccei-Quinn symmetry as follows. So this extra singlet complex scalar field should have Peccei-Quinn quantum number 1. The Higgses, whose wefts give rise to the masses of the down quark, of the down quarks, has a Peccei wind charge xt. The one to the up quark, the Higgses, which give masses to the up quark or up quark type quarks, have minus xu Peccei wind charge, and the right-handed down quark mass have this associated Peccei wind charges, and the right-handed up types have this kind of charges. And one requires that xu plus xt is equal to 2. These kind of interactions, they leave the Yukawa interactions of the type 2 Higgs doublet model invariant. And now one can do the same exercise as before in the KSVZ model. One writes down, one integrates out the sigma field. When you integrate out the sigma field, you have again to do chiral transformations in order to get standard mass terms from this from these Yukawa interactions. And at the end, you can read off from in this theory. So here it should be not the Kim, Schiffman, Weinstein, it should be Sitnitsky signed, excuse me. So that here should be Dfset. The effective Lagrange at energies below the electroweak symmetry breaking scale, but above the Qcd scale, will have this familiar form. So what is now predicted here is that this coefficient of the coupling to the model dependent contribution to this coupling to photons is 8/3, and one can also read off, so to say, how to relate this V sigma to the symmetry breakings or FA to the symmetry breaking scale. So it's not V sigma itself, but it's V sigma over 6, where 6 is a so-called domain wall number. So maybe I will talk about this later when we discuss about cosmology of this theory. The coupling to the electron is equal to the coupling to the down quark masses. This is why is this like that? It's because it's a type 2 Higgs doublet model where the leptons get the masses from the same Higgs, which gives masses to the down quark type quarks. And so this coupling goes like sine squared beta over 3, where tangents beta is defined as the ratio of the wefs of this up type quark Higgs divided by the wef of the down quark Higgs. And the couplings to the up type quarks goes like cosine squared beta over 3. So this is the prediction of this model. Note that here is also that in this model, which is important, in this Dfset model, one has also the axion has a 3-level coupling to the leptons, to electron, muon, and tau, which is not the case for this KSVZ type things. And this arises just because also why does it arise? Yeah. And this inherits from these Yukawas. And this means then that the effective Lagrangian of this Dfset model at energies below the Qcd scale will have now this coefficient 8/3 plus this model independent contributors 8/3 minus 2, and the nucleon couplings get now also extra model dependent pieces, so to say, which are now also which depend now on this beta. Okay, so this is this Dfset axion model, and now one can still, as we have emphasized before already now several times, neither this KSVZ nor this Dfset model gives a prediction of this of the Peccei-Quinn symmetry breaking scale. So the Peccei-Quinn breaking scale is a free parameter in this game, and so this is of course a bit. It would be nice to have such a prediction because it would be much easier to make to go for it. Now. This is different for this model, which I'm now talking about. This is an SO10 cross U1 Peccei-Quinn symmetry GUT grand unified model. Now, in grand unification, we have even more scalar fields, not only 2 Higgs doublets, but there are many big representations of the gauge fields. This arises from the fact, of course, that we have to break down the original big gauge symmetry from SO10 down to the standard model SO3 cross SO2 cross U1, and then finally, of course, to the SO3 cross U1 and U1 electromagnetic. So, and there are different routes. If one wants to have a gauge coupling, and these different routes employ different kind of representations of scalar field representations to break the symmetry. And one very popular route, is to break the SO10 via 210 Higgs multiplet of the SO10 down this route first to the Patti-Salam gauge group SO4 color cross SO2 left cross SO2 right, and then and then down again, always with this 210 down to the standard model SO3 cross SO2 left cross U1, employing in the last step a 126 Higgs representations. Then we are there, and then we can break this down to the SO3 cross U1 by employing a 10 Higgs multiplet. So with this kind of very big scalar representations, one can come down from break the SO10 down to the standard model, and it's well known that if you take this kind of route, then and you have this intermediate intermediate scale, then the gauge couplings then they can unify finally. So they evolve. We can go from the low energies. So these different gauge couplings, they can unify then finally at the grand unification scale of 10 to the 17 GeV or so. Now, a nice thing about this SO10 GUTs is that with 3 copies of the fermionic 16 representation, you get automatically the neutrino masses and mixing. So at low energies, you have the neutrinos involved, so to say, the right-handed neutrinos, and and you get automatically biogenesis via leptogenesis. And also, and if you impose now in addition a Peccei-Quinn symmetry like that, so from the field content, it's very simple to impose this on this representation, to impose this kind of Peccei-Quinn transformations, on the fermionic content and on these different Higgs fields, then if you impose this Peccei-Gwynn symmetry, then the most general Yukawas, they are the Yukawa sector is much simpler, and therefore that means the predictivity of fermion masses and mixing is improved by imposing a Peccei-Gwynn symmetry. One solves automatically the strong CP problem because there is an axion, of course, arising by this breaking of this thing, and this dark matter candidate is automatically an axion, and one has not to introduce an extra scale at hand, namely the axion decay constant. If you just impose this kind of Peccei-Gwynn symmetry on this model, then the axion decay constant is fixed. It's 1/3 the scale of unification divide of the gauge coupling at unification. And these things you can read off from this plot. So the mu is 1.4 times 10 to the 16 GeV, and alpha u is 33.6. So then inserting this, so the square root of lambda is essentially this m pi over m pi times f pi. This the square root of chi. This is the topological susceptibility in Qcd, but it's nothing else than this m pi times f pi over Fa. So here is determined now by grand unification. It's 0.74 nanoelectron volt. So you have really a very light axion. This is because now essentially this Fa is determined by the grand unification scale. Now it's not as simple because I mean it looks like that there is only one point, but in principle you have to take into account the full scalar spectrum. So this curve have just neglected all the threshold corrections which you get if you have a more complex scalar spectrum and you have to scan over this parameter space. Therefore, then taking into account the scalar threshold corrections and constraints from black hole superradiance and proton decay, you get at the end this as the viable. This is the viable space for the grand unification and VBL and NBL, and so this brings you then in a mass range between 0.02 nanoelectron volt and 2.2 nanoelectron volt. It's narrowed down, but here so in this grand unified theory you get a prediction for the axion for the Peccei-Gwynn symmetry breaking scale, because it's tied to the grand unification scale, and it's quite small, of course, because the mass goes like 1 over Fa. Nevertheless, it may be broke by axion dark matter experiments, as we will hear later. So here is the prediction, generic prediction of the Qcd axion for this coupling to the electric dipole moment. And now here in this line, so this is the prediction of an SO10 GAT axion. And there are experiments, proposed experiments like this Caspar electric, which look in phase 2 in this mass region. So in principle, this can be checked in the future. Now here we have already seen. Now we have seen axions which can have a mass of nanoelectron volt. Now naively, so if you go with the, so you would think in this normal UV completions, you would never go with the Peccei-Gwynn scale above the Planck scale. And as I said, so the formula for the axion mass, the standard formula for the axion mass is 6 millielectron volt for an Fa of 10 to the 9 GeV. So then for an Fa of the 10 to the 19 GeV, it's 10 to the minus let me see. Let me see. So we have 10 to the minus 3 electron volt. If you go to the Planck scale, then we have 10 to the minus 10. Now we have to 10 to the minus 13 electron volt. This is somehow the limit, the 10 to the minus 13 electron volt. This would be the limit for such an axion. Is it true that this is a limit? It's not, because now at the very end I want to discuss an axion which can even have a smaller mass. How can this be? Let us, and the construction is a bit cumbersome, but nevertheless so this kind of model was proposed by Anson Hook. So you are considering a set n axion in a mirror world extension of the standard model. Now, so he proposed to consider now n copies of the standard model that are interchanged under a set n symmetry, which is nonlinearly realized by the axion field. So you say under this Pechet-Gwynn symmetry, this standard model, the standard model in the case sector is mapped into the standard model in the k+1 sector modulo n, but the axion is so to say transformed by a plus 2 pi k over n times fa. So it has a nonlinear shift, this axion. And then you can of course then ask them, what is the most general Lagrangian implementing this symmetry? So this describes n-zero mirror worlds whose couplings take exactly the same values as in the standard model, with the exception of the effective theta parameter. For each copy of the effective theta value, for each copy, the effective theta value is shifted by 2 pi over n because of that. With respect to that in the neighbor k sector. So the Lagrange is given by for each k we have the standard model plus an alpha s over 8 pi Qcd dual term, but in each sector it's shifted by 2 pi over n. Now if you now consider then so this axion, so to say, this lives, or this living, so these different standard model copies, they live on their own, and they are only communicating with us, say k equal to 0, with the k equal to 0 world via the axion. However, so each QCD K sector contributes now to the axion potential because it's coupled so this term, which then in leading order chiral expansion, it's just the sum of all these cosine potentials. Now, curiously, if you do it, so if n is odd, the strong CP problem is solved. The potential has n minima located at 2 pi L over n Fa, including the origin A equal to 0. So it's really, so it solves the strong CP problem, this axion, but at the price at 1 over n places. And then, but then if you now consider and calculate what is the axion mass of this theory, you can do this. You can calculate this in the large n limit, which is already valid at n equals to 3 or so. It's given by this formula, which means which means that which if you calculate the second derivative, which means that the axion mass is so to say exponentially smaller by a factor z to the n half as compared to the canonical axion mass, where z was the mu over m down was equal to 1/2. So it's exponentially smaller by a factor 2 to the minus n half. So here is this behavior. So this axion is exponentially smaller. It solves the strong CP problem. One had to introduce copies of the standard model, so a very complicated hidden sector for it. But the rest is done by symmetry and it's technical natural. So the interesting thing about this model is you get an universal increase of all the axion couplings to the standard model by this factor 2 to the n half. So instead of the, for example, so this is essentially the coupling to the dipole moment of the nucleon. You get for each n for each odd n, you can populate all this parameter space. You can populate this parameter space to the left of the Qcd axion for in the coupling to the photons, and also in the coupling to the nucleon. So in principle, this gives you even a candidate for the axion at masses, solving the strong CP problem at masses much less than the one for the naive. If you just take a UV completion with Fa or V sigma less than the Planck scale, the highest mass should be at 10 to the minus 13 electron volt or so. And here you can get axions with masses down to 10 to the minus 20, 21, 22, which is the realm of the so-called fuzzy dark matter, or sometimes called fuzzy dark matter. So even the fuzzy dark matter can solve the strong CP problem in a sense. And this I found amusing. This was such a model was not there before. So this model introduced by Anson Hook is very remarkable in this respect. So again, let us make a break here, and I ask for questions. So then we switch gears, and as I promised, so I mean there are strong bounds on this Pecek-Winn symmetry breaking scale, or the axion decay constant, coming from astrophysics. And this is what I want to talk the rest today about that. So there are these very strong stellar energy loss constraints. So as has been emphasized by Georg Raffelt and others, is that stars can be really a very good laboratory for light weakly interacting particles like axions or neutrinos and so on. And namely, because the evolution of stars is very sensitive to additional energy losses. So normally a star evolves, so to say, from in this so-called Hertzsprung-Russell diagram, or surface temperature versus luminosity diagram, along the mean sequence. And for example, a solar mass star, after some time when the helium, the hydrogen burning phases out, it starts to leave this main sequence, and it undergoes and it first goes into a status of a subgiant, then into a red giant in helium burning star, a double shell burning star, and then blows off in terms of a planetary nebula and ends up as a white dwarf. And for more massive ones, they end up in black holes. Now, and in go via supernova into black holes. And this evolution of stars is very sensitive to additional energy losses. And on the other hand, it can be very nicely quantified or seen or tested in terms of this kind of brightness luminosity diagrams of globular clusters, because globular clusters are so to say that here the stars are all of the same age, and then one can observe or count, so to say, the number of stars in certain positions along the main line, and then in the red giant branch, and then in the tip, and so on. So so if, for example, now if you look in a star when it's a red giant, then particle emission will delay the helium ignition and will increase the core mass, for example. Or if you have a horizontal branch star, here horizontal branch star, the particle emission will reduce the helium burning lifetime, and this will end up in a reduction of the number of helium burning stars. So if you have enough globular clusters, and you can make this or very detailed information about the globular clusters data, then you can make these number counts and make limits on the existence and energy loss due to the production or particle emission of axions or other very light particles. Now, so how can axion be emitted from stars? So there is one way, of course. Axions may be produced in the stellar plasma by the Primakov process, by this two photon interaction, and then they leave the interior of the star just unhindered. So this is one thing. So the stellar emission could be sensitive to this photon coupling. And but axions may also be produced in stellar plasma by Bremsstrahlung. So and in this case, the relevant interaction is the electron coupling of the axion. So and in different star phases, one is in the star phases in the evolution, one is more sensitive to one or to the other coupling. So by an investigation of the number of helium burning stars versus the number of red giants in the color magnitude diagram of globular clusters, and the finding that this agrees with the prediction of the standard model, Ayala et al. Established an upper bound on the photon coupling of axions around 7 × 10⁻11 GeV to the -1, and this is this bound which you see now in many of these plots, which is called a horizontal branch. So this bound, which continues to, of course, to smaller and smaller masses, because at small mass it's essentially independent of the axion mass, and at high masses, so to say, the temperature. So at masses corresponding the temperature in the sun, which is in the keV or multi-kilo electron volt range, this production process loses its steam, and therefore also the corresponding bounds are lost. So, but this gives a limit of the order of 6 times 10 to the minus 11. And for standard axions like KSVZ or Dfset axion, this would mean that the mass of the axion is less than an electron volt or 10 to the minus 0.1 electron volt. Of course, for other axions, as you said, it could be different. What is more sure is maybe the translation into the 1 over Fe in the coupling constant. And as I said, this Ga gamma, this goes like alpha over Fa. So this alpha over 2 pi is a factor of 10 to the minus 3. So if you translate this in an Fa, this is of the order of 10 to the minus 7 GeV. An upper bound of the order of 10 to the minus 7 GeV for the decay constant of the axion. Then there is the brightness of the tip of the red giant branch in the color magnitude diagram of the global clusters agrees with the standard model. So this observable is more sensitive to the electron coupling of the axion. And the most recent determination with new data from globular clusters gave an upper limit on the axion electron coupling of the order of 10 to the minus 13 for this units ME over FA F times CAE. And so you see this is the limit in this plot. So here, what is plotted here is GAE versus the mass of the axion, and here's this upper bound of the order of 10 to the minus 13 for this coupling. And now, if you translate this in limits, for example, in the mass limit, for example, for a Dfset axion, it means that the mass should be less than a few times 10 to the minus 3 electron volt. For hadronic models, for a typical KSVZ model, it's much worse. The reason is because KSVZ model on the tree level has no coupling to electrons, and it's only a loop level induced, and therefore the limit is not as good as in the Dfset model. There are also further limits, but they are not so strong. They're not so strong from the white dwarf luminosity function, but they are also in the same ballpark. And then there are also limits on the nucleon coupling of axions. They come from the duration of the neutrino burst of supernova 1987A, and from the temperature evolution of neutron stars, which both agree with the standard model prediction. And so this give an upper bound on the nucleon couplings, and this upper bound is of the order of 10 to the minus 10 or so. If one translate this in a limit on the axion mass, it's for the Dfset axion model, it's also of the order of a milli electron volt, a bit larger, 10ths of milli electron volt. However, so as I said here, one gets very nice, one gets very strong limits, but on the boundary of these limits, there are at the moment there are even something like very small or tiny hints that there is, or that we are at the boundary of discovery of an axion. And this again, this is also so in the same observables. So that these excessive energy losses, the limits could be better, so to say, because so presently the limits from the helium-bearing stars, so they show a little excess, so to say, but it's less than a sigma from the red giant from the red giant branch stars is also a little excess, but it's not it's less than it's again not impressive. Then with some variable white dwarfs, there are stronger there are stronger indications. However, still, so nobody would claim a discovery with that. But so one could see that this as maybe there is something going on. And in fact, so if one now tries to combine the data, so to say, and try to make a combined fit in order to assemble more of the data, one finds that one can make a common fit to the white dwarf, red giant branch, and the horizontal branch data, and the common fit gives a nearly 3 sigma excess in terms of the axion electron coupling, but still less than 1 sigma excess in terms of the photon coupling of axions. So here is no information about the mass. The mass should, so in this case, the mass should be just less than the typical temperatures in the stars, and then a keV or so. So there is no information about the mass about this, but only about the size of the coupling. So it would be interesting to have experiments which probe the axion photon coupling at this level, and as we will see, ALPS2 and IAXO are probing. ALPS2 will probe this such a coupling, or nearly such a coupling, in very near future, and IAXO will also study or probe this with even much higher sensitivity. There are other hints on the existence of an axion. They are arising from the excessive transparency of the universe for TeV gamma rays. So there are a number of blazars which are observed with Cherenkov telescopes on Earth, and the spectra of these blazars is determined by these telescopes, and the measured spectra should show a dip or a break, so to say, in their spectra, arising from E plus E minus pair production at the extragalactic background light, which there is extragalactic background light in the universe, and on the way from the source to the Earth, for TeV gamma rays, the rest energy in the system of this extragalactic background light exceeds the production of the threshold energy for E plus E minus pair production, and therefore there's one, even if the intrinsic spectrum is a power law of these blazars, one should observe a break at TeV energies. However, such a break is not really visible in the spectra, and this has been interpreted, and one could explain the non-observation of such a break feature. One could interpret this as a sign that there is this non-observation that there was axion photon conversion in the so to say, when the TeV photons were traversing the extragalactic or intergalactic magnetic fields, they can convert into axions, and by this two photon interaction, and then reconvert near the Earth again in photons, and thus they could be, so to say, for them, the extragalactic background light would be transparent, so to say. And if one looks what the necessary photon coupling to have this effect is versus the mass of the axion, is that in this so-called in this blue, or in this bluish regions, which are using whose determination have used different assumptions regarding the intergalactic magnetic field and that in these regions, couplings in these regions would explain the non-observation of this. And what is interesting, that these are similar couplings. These are couplings of the order of few times 10 to the minus 11 GeV to the minus 1 photons couplings. And in this mass region below 10 to the minus 7 electron volt, this would be at the same, such axions with this kind of couplings would at the same time explain this anomalous transparency of the universe for high energy gamma rays and the anomalous energy loss of helium burning stars. So this is but fortunately, because these are only very small hints, we have this ALPS-2 experiment very soon. We'll be testing this region, and we'll be seeing whether there are axions in this parameter regions or not. So this is with this I'm finishing for today, and tomorrow we will switch gears again, and we will talk about axion dark matter.
Okay.
So the floor is open for further questions or comments or anything. Everything was clear?
Probably, yes, it was very interesting.
Okay, very good. So then I will now put this together and send it to you, and then you can upload the lecture.
Very good, very good. And for the students, okay, for the students, think about the question, because you can also ask the question then at the next lessons.
Yeah.
Or starting. Okay.
But the questions are also asked by the by my tutors, or?
Of course. They can also ask to them.
Okay.
Why not?
Okay.
So
good.
Thank you very much.
Okay, you're welcome.